This is the final presentation for Group 10 for the project's boat gyro stabilizer. This is Ryan Kappelman.
McCabe Radswell.
Logan Wolbeck.
Justin Davis.
Joshua Curry.
So starting out with some considerations, those being social and global, ethical and professional. One of the largest aspects of this project was the gyro's effect of stabilization, which also affects the comfort and operation of the equipment on board, also longevity of all that, cargo stability. So other stabilization can be damaged much easier. Maintenance cost is reduced as an effect of that. Energy savings and also materials used. It's a very simple, straightforward system.
As for motivation, the main, as was mentioned, comfort. Many people have seasickness, and the stabilization allows for many people to enjoy the water much more than they would have been able to before, allowing for much more masses of people on the water and for cruise ships. While at the same time, it also allows for stabilization, which helps with reduction of deterioration, which is very helpful for large cargo vessels carrying large amounts of shipping containers all around the world to keep them from tipping too much or for them falling apart. There also is the autopilot, which uses gyros not as stabilizers, but uses them for detecting the movement in the either horizontal or vertical planes and figuring out where to go. Because of this, there are many patents made from this. You can see two of them listed here, showing how they're oriented in the boats, right in the center and in line to keep them from moving. And the last picture shows how it would work with different yaw and pitch.
So the methods that we followed was figuring out the specifications that we would be using. And these were mainly the gyro's angular momentum, which would be either pointed straight up or straight down, and the impulse caused by a wave hitting the side of the boat, which would cause the gyro to either tilt forward or backwards. This was then led to the dynamic system equation of d theta plus L naught theta equals L sub W, which is L is the angular momentum, where L naught is the gyro's angular momentum, and the L sub W is the impulse caused by the wave. Since we had a linearized system, or we were supposed to, our system was already linear as is, so there was no further linearization needed, which led to a transfer function of theta S equals 1 over S plus L naught, and when that was solved, it led to a equation of theta T equals L naught e to the negative L naught times the time. And this led to a block diagram of simply the input impulse times the transfer function equaled the theta S, and the steady state remained mostly similar to the initial state, as the gyro's angular momentum was already extremely large compared to the impulse caused by the wave. The stability, we were supposed to use Routh-Hurwitz, but that did not apply to our system, as Routh-Hurwitz only applies to a second order system, where ours was only first order. But we can assume that our system is stable as the time response eventually goes to 0 as t gets large. And our frequency response can be seen from the Bode and phase, the Bode diagram and phase to frequency graphs seen on the right.
Now for the results, you'll see a frequency response model on the very top one. one, we have a very high magnitude, and I don't know if you can see it, but that small yellow line is our response, which is amplified in the graph below. Oh, but this we can infer that this is kind of what we want, because even with a large impulse wave happening, we see a very, very small response from the transfer function. And this is what we want with the gyro stabilization. Next. Now with the Simulink model, we've had some trouble. Ryan's probably better to describe this too.
So there was some issue trying to figure out the animation aspect, but we were able to figure out the basis of it. So if you look at the picture on the bottom left, this is the general consensus of how it moves, where you have the impulse, which would be the wave impulse and the impulse size multiplied by each other. And then that goes into a PID and a transfer function, which would then create the graph as can see in the top right. The impulse size of this graph on the top right is 2,500 Newton meter seconds. And this is only a response of 0.7, which is to be expected because the impulse is trying to fight the gyro, but the gyro wins easily because it has such a large angular momentum.
And then to conclude, and some of the future work that we would conduct here, for this, we'd like to work more on our Simulink model. And we, as a team, were able to recommend gyros for smaller boats. For future work, we would like to continue the analysis on fins and more on nose stabilization, kind of to see more of the other aspects of stabilizing boats, as well as some of the issues that we had. High expectations with little instruction, sort of like what Ryan was talking about. We had issues creating a Simulink model just because of a lack of, for a lack of better terms, help. So a lot of the time we spent as a team just trying to figure out creating these models.
And that is the final presentation for Group 10.